Hi everyone, welcome to lecture 8.1 of our Möbius inversion mini-series. In the earlier lectures, we stay mostly in number theory. We build up Möbius function mu, Dirichlet convolution, and the inversion formula for arithmetic functions. Today, we move into combinatorics. Instead of counting integers, we'll count strings over an alphabet of C colors. And we'll ask a very natural question: which strings are truly primitive, and which ones are just repeats of a shorter pattern? Now, the key idea is that every string of length n has a minimum pair d that divides n. All right, so that's the key. This gives us a clean divisor-sum identity here, and then we use Möbius inversion to isolate the primitive counts a of n. This is one entity we're interested in finding. To get the most out of this lecture, try to keep two viewpoints in your head at the same time. First, the combinatorial side. When you see a specific string, ask yourself whether it is just a shorter block repeated. For smaller n, it is worthwhile pausing the video, writing down all the strings, and grouping them by their period. Now, second, for the number theoretical side, think of n as carrying a whole divisor structure with it. For each divisor d of n, there is a layer of strings whose minimum period is exactly d, and the total c raised to the nth power is built by stacking all those layers together. Now, Möbius inversion is going to connect these two viewpoints. The divisor-sum identity tells how total C of n are assembled from primitive counts, A of d, and the Möbius formula runs that relation backwards, canceling out the contribution from shorter periods to reveal A of n. Now, if you can, pause as example n equals 4 or n equals 6, and actually check the counts yourself. So this is really important. Make sure you understand it before you go to the next lecture. Now let's go right into it.
Let us warm up by remembering how Möbius inversion helped us untangle divisor sums in number theory. We previously looked at functions on the integers where we summed values over all divisors to get a new function. The guiding philosophy was that complicated totals are built by stacking simpler building blocks. Today we replace integers by colored strings with C possible symbols in each position. Our main object will be A of n, the number of strings of length n that are not made by repeating a shorter block. With that idea in mind, we are ready to ask the same primitive versus non-primitive question for strings. Let us test your intuition with a few short strings. Here we look at three strings built from two symbols, which you can think of as 0 and 1. The string 0101 clearly splits into two identical blocks 01. 4 zeros in a row are just a single symbol repeated again and again.
This last string does not seem to break nicely into equal blocks, so it feels new or primitive.
Next, we will make this idea of repeating a block precise by defining the period of a string. Now let us give a name to the length of a repeating block inside a string. We say a string has period d if we can cut it into equal pieces of length d, and every piece looks the same. In that case, the total length n is just some whole number of copies of that basic block laid in a row.
So a number d can only be a period if the string length n is a multiple of d.
Among all possible periods, the minimal period is the smallest block size that still tiles the string exactly. Once we know the minimal period, we can think of the string as repeats of a primitive block of that length. Here are the key facts about minimal periods and our main definition. Combinatorics on words tells us that for any finite string, there is at least one repeating block size that works, and among them, a smallest one. That smallest period is unique for each string, and its length must divide the total length n exactly. When the minimal period d is strictly smaller than the length, the string is just several repeats of a shorter basic block. We call a string primitive when its minimal period equals its full length, so it cannot be written as repeats of anything shorter. We define A of n to be the number of primitive strings of length n built from an alphabet with C possible symbols.
So every string falls into exactly one bucket labeled by its minimal period, and A of n counts the ones in the bucket where the label equals n.
Now, we use minimal periods to express a simple counting formula. For each of the n positions, you have C color choices, so there are C to the n strings in total. Using minimal period, we can partition all strings into groups where every string in a group shares the same minimal period d. By definition, A of d counts the strings whose minimal period equals d.
Since any period length has to divide n, we only need to consider divisors d of n when we add up these groups.
This equation states that the easy total C to the n is obtained by adding up the contributions from each minimal period d. This gives us a textbook divisor sum, ready for Möbius inversion. We now plug this divisor sum into the general Möbius inversion framework. Möbius inversion starts with a situation where a function f of n is obtained by summing some more primitive function f over the divisors of n. The theorem says that knowing all the totals f is enough to solve back for each primitive value f of n. In our context, f of n is the total number of strings c to the n, and f of n is the primitive string count a of n. Applying the inversion formula gives a clean expression for a of n as a signed combination of powers of c. The first line is the generic divisor sum, where totals f of n are built by adding up the contributions f of d over all divisors of n. The second line is the Möbius inversion formula that recovers the primitive values f of n using the Möbius function mu. When we specialize to strings, this last equation tells us how many primitive strings of length n there are over an alphabet with C colors.
So the Möbius function is acting like a clever inclusion-exclusion that cancels out the contributions from non-primitive repeats.
Let us see the formula in action for a small concrete case. We work with an alphabet that has just two symbols, 0 and 1. Our strings will have 4 positions, so there are 2 to the 4th power, that is 16 total binary strings. We apply the Möbius formula for a of n, summing over the divisors of 4, which are 1, 2, and 4. Then we double check by grouping all 16 strings according to whether their period is 1, 2, or 4. In the formula, mu of 1 is 1, mu of 2 is minus 1, and mu of 4 is 0, so the total becomes 16 minus 4 plus 0, which equals 12.
So there are 12 genuinely new binary patterns of length 4, and the other 4 strings come from repeating shorter blocks.
Before we move on, let us summarize what we have learned. Every string of length n over c colors sits in exactly one class according to its minimal period d. By adding up the numbers a of d over all divisors d of n, we recover the simple total count c to the n. Möbius inversion turns that divisor sum around and gives a direct formula for a of n. This idea of isolating primitive structures from easy totals appears in many topics, from word combinatorics to error-correcting codes to multiplicative functions. Next time, we will place strings on a circle so that rotating them does not change the pattern, leading us to necklaces and new divisor sums.
I see the pattern now. We hunt for natural divisor sums and then use Möbius inversion to read off the primitive pieces.
Let us finish with a quick check of understanding and a broader question. First, try pausing and use the Möbius formula to work out a of 6 when the alphabet has 2 symbols.
I will think about other settings, like tilings or cycles in graphs, where objects are built from repeating patterns and divisor sums might appear.
Using the formula, we sum contributions for divisors 1, 2, 3, and 6, which gives 64 minus 8 minus 4 plus 2 for a total of 54 primitive binary strings of length 6. As you look for primitive structures in other problems, keep the Möbius inversion tool in mind as a way to uncover them.
Thank you for your time in watching this. Please like, share, and subscribe to the channel. Of course, we always would like to hear from you. Please make your comments below.